In this tutorial series, we are going to simulate internal flow through a venturi tube. First, we will model the geometry from scratch using a standard CAD environment. And then, we will move into Ennova CFD to generate a high-fidelity polyhedral mesh. We begin by selecting the XY plane and initializing the Autoline tool. We are drawing only the upper half of the profile, as we will revolve it later. First, a vertical line for the inlet boundary, followed by the horizontal section for the inlet pipe. Now, we draw the converging cone leading into the narrowest part of the tube. Next is the throat section, then the diverging cone where the pressure recovery will occur, and finally, the outlet pipe section. We finish the sketch by drawing the center line along the x-axis, which acts as our axis of revolution. With the rough shape drawn, we apply precise constraints. We set the inlet radius to 25 mm, inlet pipe section length to 100 mm, converging section length to 40 mm, throat section length to 20 mm, diverging cone section to 80 mm, outlet pipe to 150 mm, the throat radius to 12.5 mm, and the outlet radius to 25 mm. This gives us our desired 0.5 beta ratio. Once the sketch is fully defined, we use the revolution element command to generate the 3D model. Next, we export the model in step format. Now we launch Ennova CFD. We import our step file. Once the geometry is loaded, we need to perform a visual check to ensure there are no corrupt surfaces or gaps. The next critical step in the simulation workflow is the creation of face groups, which form the foundation for accurately applying boundary conditions. We begin by identifying the entry region of the geometry and assigning it as the inlet. This is where the fluid enters the system, and precise definition here is essential for controlling flow parameters such as velocity or mass flow rate. Immediately downstream, the connecting region is grouped as the inlet pipe, representing the initial flow development zone before acceleration begins. As the fluid progresses, the geometry transitions into a narrowing profile, which is defined as the converging section. This region plays a crucial role in accelerating the flow by reducing the cross-sectional area. The flow then reaches the throat, the most critical section of the venturi tube, where the area is minimum and the velocity reaches its maximum, resulting in a corresponding drop in pressure. Beyond the throat, the geometry expands and is grouped as the diverging section. In this region, the flow decelerates, and partial pressure recovery takes place, making it important for accurate prediction of flow behavior. Further downstream, the flow passes through the outlet pipe, which stabilizes the flow before it exits the domain. Finally, the terminal face is assigned as the outlet, where boundary conditions such as static pressure are typically applied to define the system's exit behavior. All remaining surfaces are collectively grouped as walls, representing the solid boundaries of the venturi tube. These walls are essential for capturing viscous effects and enforcing no-slip conditions during the simulation. A well-structured face grouping strategy like this not only ensures accurate boundary condition assignment but also significantly improves meshing efficiency and overall simulation reliability. With the geometry faces successfully named and grouped, the next step is generating the surface mesh. Navigate to the toolbar and open the Set Surface Mesh Parameters panel. Here, set the maximum size to 50, minimum size to 1 with the refinement number of 50 and the growth ratio to 1.5. Click on the geometry to generate the initial mesh. You will see a baseline, unstructured triangular mesh appear on the surface. To create a more structured and uniform grid around the cylindrical sections, we need to apply local edge sizing. Select one of the circular edges that. Right-click and choose Set Edge Mesh Parameters and set the number of nodes to 200 and hit Accept. Repeat this exact process for the other circular edges along the geometry, including the throat, diverging sections, and outlet pipe. Once all the edge parameters are assigned, regenerate the surface mesh. A prompt will ask if it is okay to clear the older mesh. Click Yes. You will now see a much cleaner, structured surface mesh mapped smoothly along the contours of the geometry. Next, we need to create prism layers, also known as boundary layers, to accurately capture the near-wall fluid flow. Open the Local Mesh Parameters panel. In the boundary list, select all the groups that represent the solid walls. This includes the converging section, diverging section, inlet pipe, outlet pipe, and the throat. Now under the Local Mesh Setting area, set the prism to use volume and set the layer number to 10. Then, set the height to 0.1 and height ratio to 1.2. Click Apply Prism Setting Parameters. When you click Open Mesh Parameters Setting, it will open the table with assigned values in the list at the bottom of the screen. Then go to Mesher toolbar and select Inflate Mesh. It will generate the boundary layers for the existing surface mesh. After generating the mesh, you can open the Mesh Quality dialog to verify the element metrics. To physically inspect the internal mesh structure, activate the cutting plane tool to slice through the geometry. If you zoom in closely to the edges of this 2D slice, you can clearly see the 10 structured prism layers generated directly against the wall boundaries. Now, to generate the complete mesh, select the Tet Fill Mesh option. This will automatically create three-dimensional tetrahedral elements, fully defining the volume mesh of the model. After this, the mesh quality is evaluated by checking key parameters such as orthogonality and skewness to ensure the mesh is suitable for accurate simulation. To physically inspect the internal mesh structure, activate the cutting plane tool to slice through the geometry, helping verify mesh uniformity, smooth transition between element sizes, and adequate refinement in high-gradient regions, ensuring the mesh is well prepared for accurate CFD analysis. In the final phase of the workflow, the mesh is converted into a polyhedral format. Navigate to the top navigation bar and enable the Polyhedral Mesh option. Next, ensure the boundary layer option is also selected. This guarantees that the volume mesh will be created with our previously defined prism layers included. Go ahead and generate the mesh. You will immediately notice the transformation on the surface. The original triangular elements have been replaced by multi-sided, polygonal faces, giving the model a honeycomb-like appearance. Finally, to inspect the internal structure of this newly generated mesh, activate the clipping plane tool. As the view cuts away, You can clearly see the interior volume is now filled with dense, high-quality polyhedral cells. Furthermore, looking closely at the pipe walls, you can verify that the volume mesh has perfectly integrated with the 10 boundary layers we set up earlier. To ensure this new polyhedral grid meets solver requirements, open the Mesh Quality dialog. Here, review the element metrics, verifying that values like skewness and orthogonality are within acceptable limits. This seamless transition from the structured boundary layers to the highly efficient polyhedral core ensures optimal accuracy and stability for the solver. With the mesh quality fully validated and the internal domain accurately resolved, the model is now primed and ready for fluid dynamic simulation. Now, we save the generated mesh in the native Ennova CFD format as an .ecf file, preserving all mesh and boundary data. With the mesh successfully saved, we can proceed to export it for further simulation setup. To export, click on the application menu and navigate to export. Here, you will see several available export options, including StarCD, Fluent, CGNS, ISOM CFD, OpenFOAM, Ennova, and CFD++. For now, we will export our mesh in the fluent.msh format. To do this, hover over Fluent and select Export the mesh to Fluent file. When the Save dialog box appears, choose your destination folder, enter your desired file name, and click OK to complete the export. With the mesh successfully exported, the model is now ready for simulation. In Part 2, we will move into the OpenFOAM setup within Ennova CFD and define the complete solver configuration. Thank you for watching. See you in the next part. For licensing, demos, or support for Ennova CFD, contact us at sales@daysiminnovations.com.